Hi folks, see you speaking again. A couple of videos ago I presented you three distinctive versions of digital helper for Mel Robbins' role, the 5-second. And just as a reminder, because today I'm going to focus on the electronic version of it, it was just counting down by itself once the power is on, and when reaching the counting from 5, 4, 3, 2, 1, it displays a go for about 5 seconds and then it's restarting again. So you won't be able to realize how funny and rewarding this project is until you guys make it yourselves. This is why I'm presenting it to you today in detail about how to make it. So I'm gonna shut the power down. I'm taking it away from here and we're going to discuss the diagram to see how can we make it. Okay, so here it is. Don't look for it anywhere else because you won't find it. Okay, I designed it to follow exactly the famous 5-second rule of Mel Robbins. So here it is. Now, in order to be able to make it, you're going to obviously need a breadboard, and you're going to use one similar to this one, only 2 sections, and you're going to be absolutely surprised to find out how many things can you place on only 2 sections and still remaining some room here. Here in the top is going to be a connector I described some time ago, which is a IDC connector, actually a converter to mount on a breadboard. And here is a PC relay. And this one also I discussed in more than 3 videos some time ago. And then you have different integrated circuits I'm going to discuss. Okay? But first you have to start with a clean breadboard, only 2 sections. Now, there are going to be 6 steps before we check the whole diagram. And the first step you are going to do is to pick up the empty board and to connect the wires for the power supply.
I don't think so. No, 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 no. I don't think so. No, 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 no. It's never, ever, 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 ever gonna happen. I don't think so. No, 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 no. I don't think so. No, 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 no. It's never, ever, ever, ever.
Once you connected the power supply wires, the next thing, it's a good recommendation, in order to keep the wiring clean, in other words, to have not too many such of these annoying wires all around, so to be able to see through and even to take some measurements to do troubleshooting, you have to place here and there a lot of jumpers. And these jumpers are the ones having terminals of different integrated circuits related to the power supply, either to the positive 12, or to the ground. Like here you have pins number 1, number 1, number 1, plenty of pins here and there related to the power supply or the ground. So this is going to be the step number 2.
I don't think so. No, 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 no. I don't think so. No, 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 no. It's never, ever, 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 ever gonna happen. I don't think so. No, 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 no.
Now for the step number 3. Before I'm describing the functioning of the diagram, just to make you starting the wiring, I'd like you to notice here the presence of 3 integrated circuits 555. If I'm picking up the one in the top, the circuit right here in the top, left, the package 555 is arranged in a astable or clock generator arrangement. There are 3 components counting for the calculation of the frequency or for the period. R1 in the top is 22 kilo ohms, R2 in the middle 33 kilo ohms, and in the bottom here a capacitor 22 micros. Now I'm opening an application here I already used with you last time. Okay, let's find it. So right here for the A-stable operation with 22 kilo ohms R1, 33 kilo ohms for R2, and 22 microfarads for the capacitor, you're going to get a frequency of 0.75 hertz. When you convert it in period, in duration, it's 1 over frequency. 1 divided by 0.75 is about 1.35 seconds. So I've made it a bit longer than 1 second on purpose for you to have time to see the counter working fine. We're going to find out. So step number 3, we wire the A-stable circuit.
I don't think so. No, 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 no. I don't think so. No, 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 no. It's never, ever, 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 ever gonna happen. I don't think so. No, 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 no. I don't think so. No, 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 no. It's never, ever, 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 ever gonna happen. I don't think so. No, 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 no. Maybe someday you'll have it your way.
Next step, number 4. The next two 555s are used as monostables. Monostables, from the 0, they just deliver 1 pulse you can control and they go back to 0 after that. So the monostable here in the top, if I pick it up, so I have here a resistor at 330 kilo ohms, 330 kilo ohms, and the capacitor 10 microfarads. So for these ones, you should get around 4 seconds. So because the components may have some tolerance, you may get anywhere between 4 and even 5 seconds. The capacitors are usually a bit higher than the value printed on the body. Okay, so when we wire this one, we should get approximately 4 up to 5 seconds. So we're going to wire the monostable in the step number 4.
I don't think so. No, 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 no. I don't think so. No, 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 no. It's never, ever, 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 ever gonna happen. I don't think so. No, 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 no. I don't think so. No, 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 no. It's never, ever, 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 ever gonna happen. I don't think so. No, 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 no.
Step number 5 is to wire the next monostable. This one has a very short time because the capacitor here for this one is only 1 microfarad and the resistor is 22 kilo ohms. So with 22 kilo ohms and 1 microfarad, take a look what do you get, about 25 milliseconds. So about 25 milliseconds, I wrote that value here just to make sure you're going to get it, okay? And at the end, of course, I'm going to explain how are they interrelated. But now we have to wire the monostable using the 555C. Is going to be the step number 5.
I don't think so. No, 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 no. I don't think so. No, 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 no. It's never, ever, 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 ever gonna happen. I don't think so. No, 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 no. I don't think so. No, 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 no. It's never, ever, 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 ever gonna happen. I don't think so. No, 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 no.
Once you have the 3 555s wired on the breadboard, then we can focus on the counter and the associated circuits around it. Actually, if you pay a bit of attention about this counter, I used it already, I described it in detail some videos ago, and I've made already some projects here. We have a counter It's a standard 193. I'm using the CMOS version 4193. Here we have a RS flip-flop, and I'm going to talk about that a bit later. So an RS flip-flop, and because the package containing it contains 4 identical gates with 2 input each, I have here 2 other gates belonging to the same package. And then here I have a exclusive NOR gate. This is a kind of decoder for the number 0, which I'm going to explain a bit later. And this one is like a decoder for what is going to become the letter G. So we're going to wire now the counter and the associated circuits around it, one by one, taking our time before I'm telling you how this is all is gonna work.
I don't think so. No, 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 no. I don't think so. No, 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 no. It's never, ever, 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 ever gonna happen. I don't think so. No, 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 no. I don't think so. No, 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 no. It's never, ever, 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 ever gonna happen. I don't think so. No, 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 no. Maybe someday you'll have it your way. Maybe someday it'll all work out. Until then, nope, a nope, a nope, a nope, definitely nope, a nope, nope, a nope. Probably never, ever, 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 ever gonna happen. Oh no. Nope, a nope. Probably never, ever, 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 ever gonna happen. Oh no.
At the end, when you did all the wiring, you're going to get this one. But guess what? Just because it's very funny to make it, I wired it especially for you, the second one, because I did not dismantle the first. And the best way to check the new one is actually to make them working both together. And then we're going to see some tips and, let's say, ideas for troubleshooting, because troubleshooting is going to be required. Okay? So let's come closer to find out. I'm going to connect this one to the display. Okay, it's the same display used before. Okay, so the same display used before. Let me just disconnect. Okay, so now if I connect this one over here, the positive, then the negative, and then I'm gonna give it power. Okay, and I'm gonna put it over here. We're going to see here how it's operating. So it stays about 5 seconds, and then it says 5, 4, 3, 2, 1, and go. And it stays for about 5 seconds and so on. And guess what? I'm gonna make it even nicer. I'm going to connect both of them all together to find out some tips and ideas for troubleshooting. So let me disconnect it. I'm gonna place it over here. I'm gonna leave this one with its display, like that. And this is the one I connected weeks ago when I presented it first time. So we're going to connect the power from one to another. So we're gonna get both of them powered. And I'm gonna connect a standard display. We're gonna see what does it mean, a standard display, on this one. So each of them is going to have its own display. So now the power supply for both is going to be the positive and the ground. So plus 12 volt is the power supply for both. And just to make it a bit more visible, something like that, okay? So power on. Okay, so then we're going to see this one already reached the go. This one also reaches the go. So each of them in their own rhythm. Why is that? Because of the tolerance of the components, they don't respect exactly the duration of the pulse, about 1 second and so on. It's around, okay? But I want you to see that both of them are working just fine. So they are identical projects, okay? And I just wired the second one for the fun of it to see that it's really doable. Now, we can talk about diagram and a couple of things related to troubleshooting. The counter has two counting inputs, two clock inputs, counting up and counting down. The counting up is not in use, so to keep it idle, it's connected to plus 5 volt. Pulses are received on the counting down. This is why, after the go stays there for 5 seconds, the circuit starts to count back, down, up to 0. Why does it start to count to 5? It's starting to count actually from 5. This is the famous 5-second rule, okay? Because on the parallel inputs here, which are on the pins 9, 10, 1, 15, I connected them like this. Number 5 in binary, it's 0, 1, 0, 1. So the pin 9 connected to 0, which is the ground. Pin 10 connected to positive 12. Pin 1 to ground. And pin 15 to positive 12. Low, high, low, high. That's how you can make it. So it's like preset to the number 5. In order to have it preset, you have to have the load falling in 0. We're going to see what happens. So now let's suppose it's receiving pulses from here, from the A stable. So it's receiving pulses down 4, 3, 2, 1, and back to 0. When it's reaching 0, this pin here, which is borrow, the pin 13, it's suddenly falling in 0 shortly. But this is becoming something we call the reset of the RS flip-flop. What does it mean, the reset? The normal output, which is here, becomes 0. This is the meaning of the reset. So becoming 0, if you take a look on the wire over here, this pin 12 of the NAND gate becomes 0. So whatever is coming from the A stable circuit here, the pulses, they don't pass anymore to count down. So this one really stops working. But to make sure of that, this one is a 0. But this is the normal output Q. The complementary output Q bar becomes a 1 because they are opposite to each other. And if you follow this wire here, going to the base of a PNP transistor, when this one is a 0 and this one is a 1, is about 10 volts, 10 to 12 volt. 12 volts coming here on the base of the transistor is preventing it from working. So preventing it from working, the circuit, the 555, is not powered anymore. So this is just to make sure that there is no chance for the pulses to come by, okay? But then, at the same time with this, when this one became a 0, here exactly in this point is going to trigger this monostable circuit. And this is why the display stays 5 seconds on go, because of this monostable. But when the 5 seconds are gone, this one here at the output, take a look where it's going. It's going in 2 places. First, it's going here on the input on the input set of the RS flip-flop. Input set meaning the output Q becomes a 1. So by becoming a 1 on the pin 12 is allowing pulses to come by. At the same time, the second action is doing from here, from the output, it's going to the second monostable, which just delivers a very quick pulse. I've made it a bit longer. Instead of 0.1 second, I've made it 25 milliseconds. So this one goes right here on this exclusive NOR and giving a 0 on the load to allow the number already preset on the parallel inputs to be loaded again in the counter. So in the moment the pulse of 25 milliseconds comes here, the number 5 is inscripted again inside. So this is why by receiving pulses on the counting down, the counter is replaying the counting down 5, 4, 3, 2, 1, 0. So this one I clarified. Now this part here, this is a kind of decoder for the number 0. But take a look how interesting it's becoming. Here is the least significant digit, the one which is going to count 5, 4, 3, 2, 1, 0. But during this time, the second digit is not energized at all. How may this happen? It's simply because if I'm just making it quickly over here, a standard 7-segment display is going to be like this. A, B, C, D, E, F, and G. And the most of the decoders, when receiving a signal like 1111, they're gonna make this display blank. And this is why it stays blank. Now, how come suddenly it shows the letter G? I don't know if you noticed, this is the letter G. But if you take a look here at a standard display, and now I'm explaining you what does it mean a standard, it's actually the number 6. Take a look what happens. The display I'm using is actually not a standard 7-segment display, but it's a 16-segment display. The ones in the top, these ones and these ones, which are the H, J, K, L, M, and N, I'm not using them. However, in the top, the segment A is made of 2 subsegments, and they are called A1, A2. Here is D1, D2. And here in the middle, you have G1 and G2. So in order to come from the number 6, when you power both G1 and G2, exactly like you're going to see here soon, 1, and now is a 6. What happens here actually is a G. Why? Because I simply disconnected the segment or the subsegment G1. So only the G2 remains energized. This way, you're going to have displayed this kind so this is the G, you see? So I converted 6 into a G by disconnecting only for the purpose of that project the segment G1, okay? But how is this happening is because of the presence of that particular relay over here. What happens is, in the moment you reach the number 0 when counting down 5, 4, 3, 2, 1, 0, from these 4 wires, they go to the least significant digits. So yes, it's displaying a 0, exactly like here, and the 0 has a resemblance with the letter O. But at the same time, what happened was, before this one reaches a 0, what's coming on the 4 inputs of the decoder inside my big display on the second digit? These 2 wires, B and C, are permanently connected to +12. So they stay exactly like here, like I say here, D, C, B, and A. The B and the C are permanently one logic. And through the normally closed contacts of these 2 groups of the relay, you also get 1, 1. 1 on the D, 1 on the A. So this is why the display stays blank, because it has 1, 1, 1, 1, which is actually representing the number 15. Okay? In the moment the number 0 appears over here, what happens is, let's say this particular AND gate, the 4082, is a kind of 0 decoder. So decoder of the number 0. So when all inputs here become a 1, so we have 0, 0, 0, 0. At the other end of the inverter, you have 1, 1, 1, 1. So because it's an AND gate, 1 times 1 times 1 times 1 is a 1. In that moment, the NPN transistor here becomes energized, becomes a switch. So this relay is going to be energized. What happens then? The two contacts normally closed are opening, and the common goes connected to normally open and normally open. But the two contacts normally open are grounded. But grounding them is a 0. So you're going to convert this into 0, 1, 1, and 0. And this is the number 6. But instead of displaying the number 6 like over here, let's wait just for a second to see it. You see the number 6? By disconnecting the G1 subsegment, it's becoming the letter G. And this is why you can see here a G and here the letter O, equivalent to the number 0. So this is why it displays a go. This is how it's working. So again, don't look for this diagram nowhere else, you won't find it. But because I'd like you to make this project working, it's so funny to this. Take a look, I've made 2 of them. Not only one, but I've made 2 of them. Okay? I'm gonna put, of course, this diagram on the Google Drive to get it. Now, couple of details here because I'd like you to get it right, okay? You see here is a gate 4077, which is a exclusive NOR. If you're only lucky, because the pin numbers are the same as for the package 4001. 4001 is a NOR, is not an exclusive NOR, is a NOR, okay? For the purpose of the project, if you're lucky only, it may work with this one. If you're lucky, I have it over here. But if you're not lucky, I'm going to show you something about a troubleshooting, what may happen if it won't work, okay? So let me look for a package 4001 in order to have it right, okay? Let me see where I placed it or misplaced it. Maybe it's over here. Okay. So I have it over here, okay? If I move these 3 wires, I move these 3 wires over the 4077. I just moved these 3 wires over the 4077. And now you understand why I left some room. You see the original project is over here and there was some free room. Is because I wanted you to see what happens if you put the exclusive NOR gate, the one you're going to find in the diagram on the Google Drive, and you put the power on. Okay? You see this? It's going to work just fine. Right now. So it's a go, okay? So this is why you find it here on my drawing, the 4001, not in use, but instead I'm using 4077 because this is good to know. Now another thing to know for troubleshooting is about this one here, 4011, okay? 4011 is a standard 2-input NAND gate. And take a look. If I place such a gate, okay? Let me just stop it. Remember, don't do wiring with power on. It's not recommended, okay? Okay? So, I have another package here. This package I have is 4093. I'm going to just have it replaced by a standard 4011, okay? 4011. And when I place it here, let's see what happens. Okay, power on. Until now, everything is just fine, okay? It's starting to count, 5, 4, 3, 2, 1, 0, go. But suddenly the displays are stopping working. I'm telling you, you don't know what to do. And let's see it one more time. Apparently it's okay. But suddenly the displays go off, okay? So instead, on the diagram you're going to find on Google Drive, instead of the 4011, you're going to find 4093. It's a Schmidt trigger. 4093 is a Schmidt trigger. Luckily, both packages, 4011 and 4093, I'm going to write it here just to make sure you guys get it. Okay. Use 4093. Don't use this one. Okay. You can try with 4011 because it's a bit more easier to find, but it's only working if you're lucky. Okay. If you reach that kind of thing and it doesn't work properly, now you know what to do. You need to place a 4093, which is also containing NAND gates inside, but they are Schmidt triggered. Okay. So they were invented for a reason, and here is the reason. Okay. Because in the moment you have it mounted over here, okay, so it's counting down 5, 4, 3, 2, go, and it doesn't go off anymore. It stays there for 5 seconds as supposed to be. Okay. Then you don't have to use my relay, the Omron. You just need the double pole, double throw PC relay. Maybe the last detail I'm going to tell you is how do you connect the contacts of the relay to the IDC connector over here, because you have to know how to do it. And I'm going to use the other page to draw it. Okay. So here is a standard 16-pin connector, 8 on each side, for an IDC to breadboard. Okay. So when you place it on a breadboard, I have another one here. It's described in another video. I'm going to put a link in the description of the video. I'm going to draw the contacts here. So it has 16 contacts. I'm going to draw one like that. Three, 4, 5, 6, 7, and 8 on one side. 1, 2, 3, 4, 5, 6, 7, and 8 on the other side. Here somewhere is the notch for the connector. So I'm using these ones here for the digit number 1, and the other 4 ones here for the digit number 0. Okay. And for both of them, in the way I have my arrangement done on the display printed board, I'm gonna have their C, B, D, and A signals. C, B, D, and A signals. Okay. For the digit number 0, it's very easy. The A is coming from 4193. Actually, all of them, they come from the package 193. 193 and 4193. But the A is coming from the pin 3. The D is coming from the pin 7. The B is coming from the pin 2. And the C is coming from the pin 6. Okay? You don't have to know them by heart, but you go on the diagram and you're going to find out. Okay? The digit 0 is easy. The problem is with the digit number 1, okay? So here I'm going to put the relay. The relay is going to look like that, okay? The relay has 6 pins. For the contacts and 2 for the coil. So here is the coil. Okay, here is the coil. So for the coil, the top goes to plus 12 volt. The other end of the coil is energized from a transistor. So this is going to be the collector, the base, and the emitter of the transistor. The emitter is grounded. Okay. The base receives signals through a resistor, 10K. Okay. And this is from the 4082 pin number 1. Okay. So is right here. From the 4082 pin number 1, it's coming on the 10 kilo ohm resistor, which is this one. This is the transistor. This is the NPN transistor over here. The emitter is grounded, and the collector is just going to the end of the coil, and the other end of the coil is 12 volts. So that's how you energize the coil. Now the contacts, okay? In the way my relay is arranged, okay? What you have is this. This is the normally closed, this is the common, and this is the normally open. Normally closed, common, and normally open. So the two groups of contacts, okay? So the point about this is in the top, the second digit has the, remember, the B and the C. They are connected to plus 12 permanently, plus 12 volt, okay? So this one is going the D right here on this common, and A goes over here, over the other common, okay? So the normally open is grounded, okay? And this one also here is grounded, okay? And the normally closed, it goes to 12 volts, plus 12. Plus 12, okay? And this is how you make the, and by the way, my whole display, it has the signals here, A, B, C, and D on both digits. And here I have my ground, and here I have these two together, the plus 12 volt. The other 4 pins here I'm not using, okay? So this is how the connections are made between the relay. If you want, the relay is going to be like that, okay? The relay is like that. That's how the relay is connected to the IDC connector to make the digit, okay? So this is the diagram. These are the two samples, the one I've made a couple of weeks ago and the one I've made now for yourselves, okay? And I hope you're gonna have the same amount of fun that I had, and then be ready for the next one. Bye-bye.